Hey, welcome back dear students to the tutorial about the chemical application of group theory, and this is the part 13 video. We have been discussing about the application of group theory in molecular orbital theory. Okay, and this video is actually the continuation of the previous video. In the previous video we had discussed about the molecular orbital theory of cyclopropenyl cation. Okay, finally we reached the point that we had derived the symmetry adapted group orbitals from the atomic orbitals pi atomic orbital p pi orbitals of the 3 carbon atoms. Okay, I think you have watched the previous video. If not, please watch the previous video, then only you can understand this video. It's a continuation of the previous video. Okay, then okay, this was our last slide. That is, we derived 3 normalized symmetry adapted group orbitals. Psi1 is equal to 1 by root 3, phi1 plus phi2 plus phi3, and it has a symmetry of, okay, I think you remember, that is A2 double dash symmetry, or simply we can say symmetry of A symmetry. And psi2 and psi3 are a degenerate set having same energy, degenerate set of 2 wave function, that is 1 by root 6, 2 phi1 minus phi2 minus phi3. Psi3 is equal to 1 by root 2, phi2 minus phi3. And these two are a degenerate set having a symmetry of E double dash. It is a 2-dimensional representation. Therefore, basis will be a 2 function, a combination of 2 function. Okay, and this we have derived in 2 methods by using D3H point group of cyclopropane cation, and in a shorter method or in a easier method by using a rotational subgroup of the D3S, that is C3. Okay, then next step is, this is actually, these 3 are actually symmetry adapted group orbitals. Okay, from this we want to form symmetry adapted linear combination SALCs by a linear combination of this one. Okay, sometimes this SAGO itself become SALC. Okay, if an SAGO do not interact with any other orbital, it will be an SALC. If SAGO interact with other wave function, then that linear combination will be an SALC. That we want to check that, that we will discuss later. Now we assume, okay, we want to calculate the energy of the cyclopropenyl MOs, molecular orbitals. Assume that these 3 symmetry adapted group orbitals interact. We assume they interact and linearly combine to form SALC MOs. Okay, and that is our general method. First we form SAGOs, and these SAGOs linearly combine to form SALCs. Okay, then the trial wave function we can write it as psi I is equal to Ci1 psi1 plus Ci2 psi2 plus Ci3 psi3. Okay, and it's a trial wave function. From this we want to determine the energy and the coefficient Ci1, Ci2, Ci3 are the coefficient. Actually they are the extent of the contribution of each orbital to the molecular orbital. Okay, and this trial wave function give rise to 3 secular equation. Okay, that is C11 H11 minus ES11, C12 H12 minus ES12, C13 H13 minus ES13 is equal to 0. Similarly, C21 H21 minus ES21 plus C22 H22 minus ES22 plus C23 H23 minus ES23 is equal to 0. And third one, C31 H31 minus ES31 plus C32 into H32 minus ES32, C33 H33 minus ES33 is equal to 0. Okay, how this equation is formed into secular equation, that we had already discussed in the first video of this molecular orbital theory. If you have any doubts, please watch again the first video. Actually, this is the method we are using. That is, our equation is H psi is equal to E psi okay, or h minus e into psi is equal to 0. Okay, from that equation we are deriving this form of equation, and that's a technique that's a method we already discussed in the first video. If you have any doubt, please watch that video again. Actually, what are these h1, h1, 2, etc. are? This was the we are discussing in the first video. That is why we get an equation like this. It is a two equation. Actually, in this case, we get three equation. Okay. Actually, this HII is equal to integral phi I h cap phi I d2, and Hij is equal to integral phi I h cap phi j d2. Okay, and SII is equal to integral phi I d2. Actually, HII is the energy of the atomic orbital phi I or psi I, and Hij is actually the energy of interaction of phi I and phi j. Energy of interaction of phi I and phi j, or psi I and psi j. Okay, SII is also actually is equal to 1, and psi j actually is equal to, because phi 1 and phi 2 are, or phi I and phi j are orthonormal. Okay, and this is the overlap integral. Okay, this we have already discussed this one. Okay, clear. Then, and the corresponding determinant, this is the determinant form, we can try like this one: h11 minus cs11 plus c12 into, actually c is not needed, h12 minus cs12, h13 minus cs13, and h21 minus cs21, h22 minus cs22, h23 minus cs23, and h31 minus es31, h32 minus es32, h33 minus es33 is equal to 0. Okay, that is a determinant form. And since, as I have told you, since these three SIGS are orthonormal, S11, S22 and S33 is equal to 1. And all SIJs are 0 if I not equal to J. That is, S11 is equal to S22 is equal to S33 is equal to 1, and S12 and S32 terms like that are equal to 0, because phi I and psi I, these wave functions are orthonormal. Okay. Then another important point, since we know that the wave function psi 1 belongs to A symmetry, and wave function psi 2 and psi 3 belongs to E symmetry. Therefore, H12, H13 and H21 and H31, all these are equal to 0. Okay, because we know that, okay, we know that what is H12? H12 is actually integral psi 1 h cap psi 2 d2. Okay, and we know that the symmetry of h cap is equal to A. Okay, symmetry of h cap is equal to A, because Hamiltonian is an energy operator. Energy do not change by any symmetry operator. We have already discussed that one. Energy cannot change by symmetry operation. Therefore, h cap has a symmetry of fully symmetric or totally symmetric. Therefore, it is A. And psi 1 is also equal to A, but psi 2, we know that psi 2 and psi 3 belongs to E symmetry. Okay, so the total, the direct product of, we know that A into A is equal to A into E is equal to E. Okay, and we know that only this integral is known non-zero, or integral will be vanish only if it is a totally symmetric representation. Here in this case it is not totally symmetric representation, therefore it is equal to 0. Okay, similarly we can like h13 is equal to integral psi 1 h cap psi 3 d tau. Again in this case psi 1 is equal to asymmetry, h cap asymmetry, psi 3 is equal to E. Okay, then also here is equal to E, therefore this integral is equal to 0. Similarly in the case of h21 and h31. Okay, because psi 1 has a asymmetry and psi 2 and psi 3 are E symmetry, therefore they do not interact. That is a simple point. Okay, that means these terms h12, h13 and h21 and h31 are 0, because psi 1 do not interact with psi 2 and psi 3, because psi 1 has a symmetry of A, psi 2 and psi 3 has a symmetry of E. Okay, then the determinant reduces in this form, that is h11 minus, here ES11 was there, but S11 is equal to 1, therefore it is equal to h11 minus E. And this term was h12 minus ES12, and we know that h12 is equal to 0 and S12 is equal to 0, this is equal to 0. Similarly this term is equal to h13 minus ES13, h13 is equal to 0 and E into S13 also equal to 0, therefore this term also equal to 0. And in this term was h21 minus ES21, this also h21 is equal to 0, E into S21 is equal to 0, this is 0. And this term also, this is equal to actually this is h31 minus ES31, that is equal to 0. This whole term become 0. And here it is h22 minus ES22. Okay, actually this ES22 is not needed, because S22 is equal to 1. Okay, and here also H23 minus ES23, this term was actually H23 minus ES23, but ES23 is equal to 0, therefore this become S23. Here S32 minus ES32, actually this term ES32 is equal to 0. Actually this here only S32 is needed. Okay, here H33 minus ES33, ES33 was there, but S33 is equal to 1, therefore it is equal to E. So this was the equation. Okay, so this equation reduces in this form, H11 minus E, 0, 0, 0, 0. Okay, that is, it is block factored into a one-dimensional determinant and a two-dimensional determinant. Okay, clear. So we can solve it separately, that is H11 minus E equal to 0. And this means that the wave function psi 1 do not interact with psi 2 and psi 3. Okay, this means that is we are separating this H11 minus E, is that the wave function psi 1 do not interact with the psi 2 and psi 3. Therefore, this SAGO psi 1 itself an SALC. Okay, clear. That is, I have already told you, if a SAGO interact with other orbital, then we have to consider the linear combination as the SALC. If a wave function or SAGO do not interact with other SAGOs, then that itself is an SALC. Therefore, the psi 1 itself is an SALC because it do not interact with psi 2 and psi 3. Because psi 1 has a symmetry of A, psi 2 and psi 3 has a symmetry of E. So they do not interact. Therefore, psi 1 itself is an SALC. So we can solve this problem very easily. That is, we can solve it very easily. That is, H11 minus E equal to 0. Therefore, E is equal to H11. We want to calculate this energy of psi 1, energy of psi 1. And that is E is equal to, what is H11? Integral psi 1 h cap psi 1 d2, that is h11, and that is equal to integral. What was psi 1? Psi 1 is equal to 1 by root 3 into phi 1 plus phi 2 plus phi 3 into h cap. Again psi 1 is equal to phi 1 plus 1 by root 3 into phi 1 plus phi 2 plus phi 3 d2. Okay, actually that is E. Okay, then this is equal to E is equal to 1 by root 3 into 1 by root 3, that is 1 by 3 into integral 1 by 3 we can take an outside, integral phi 1 h phi 1, this phi 1 into this phi 1. Okay, that is phi 1 h phi 1 d2 plus again integral phi 1 into phi 2, that is phi 1 h cap phi 2 d2 plus integral again phi 1 into this phi 3. Phi 1 into h cap is here, phi 1 into h cap phi 3 d2 plus similarly integral phi 2 into h cap phi 1 d2 plus integral phi 2 into h cap phi 2 d2 and integral phi 2 into h cap phi 3 d2 plus integral 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 phi 3 into h cap phi 1 d2 plus integral phi 3 into h cap phi 2 d2 plus integral phi 3 into h cap phi 3 d2. Okay, and this is equation. And you remember one point, you have to study one point, that is integral phi I h phi I d2 is the energy of the atomic orbital phi I, and it is denoted as alpha. Okay, that is integral phi I h cap phi I d2 is actually energy of the atomic orbital phi 1, it is denoted as alpha. And integral phi I h cap phi j d2 is the energy of interaction between phi I and phi j. Energy of interaction between phi I and phi j, and that is denoted as beta. Energy of interaction between phi I and phi j denoted as beta. Energy of interaction between energy of the atomic orbital, okay, is denoted as alpha. That is phi I h cap phi I d2 is energy of atomic orbital phi I, and that is denoted as alpha. And this is phi I h cap phi j d2 is energy of interaction between phi I and phi j, and that is denoted as beta. So this become phi 1 phi 1, therefore it is alpha. This is phi 1 phi 2, this is beta. Phi 1 phi 3, again beta. Phi 2 phi 1, beta. Phi 2 phi 2, alpha. Phi 2 phi 3, beta. Is again, it is phi 3 phi 1, it is alpha. Phi 3 phi 2, it is alpha. Phi 3 phi 3, it is beta. So there are 1, 2, there is a mistake. It is not alpha. This is phi 3 phi 1, therefore it is beta. Phi 3 phi 2, it is beta. Phi 3 phi 3, it is alpha. Okay, then this is alpha, and this is the 3 alpha. Okay, and beta is 1, 2, 3, 4, 5, 6. Okay, so we get the equation, that is energy is equal to, we can write here, energy is equal to 1 by 3 into there are 3 alpha plus 6 beta. That is equal to alpha plus 3, we can take it outside, 3 by 3 cancel, therefore alpha plus 2 beta. And that is the energy of psi 1, energy of psi 1. Okay, so we have calculated energy of psi 1 is equal to alpha plus 2 beta is the energy of psi 1. And similarly, we want to calculate energy of psi 2 and psi 3. Okay, next we want to calculate energy of psi 2 and psi 3. Remember, psi 2 and psi 3 are degenerate sets, therefore their energy will be same. So that reduces our job. Okay, then our two-dimensional determinant. What was our two-dimensional determinant? This is our two-dimensional determinant, that is H22 minus E, H23, here H32, H33 minus E. And this was our two-dimensional determinant. Okay, and you understand one point, that is H23 is equal to H32, and that is the energy of interaction between psi 2 and psi 3. That is the energy of interaction between psi 2 and psi 3. Okay, if psi 3 and psi 2 interact to form a new SILC, then this H23, that is equal to H32 is not equal to 0. Okay, if they interact. If they do not interact, then H23 is equal to H32 is equal to 0, then psi 2 and psi 3 itself are SILCs. Okay, I think you understand. That is, we want to check this psi 2 and psi 3 are, these are actually SAGOs. Psi 2 and psi 3 are the SAGOs, two SAGOs. They are degenerate sets. They have same energy, but they are SAGOs, not SILCs. We want to check whether they are SILC or SAGO. Sometimes this SAGO itself, SILC like psi 1. Psi 1 is itself an SILC. Here also we want to check this psi 2 and psi 3 itself forms an SILC. How we check? If they interact, then they are not SILC, they have to combine, or we have to consider the linear combination. If they do not interact, they itself forms SILCs. And how we can understand they are interact or not? If they interact, then H23, that is equal to H32, is not equal to 0. And H23 minus, if they do not interact, then H23 is equal to H32 is equal to 0. So, how can we understand they interact or not? We want to calculate H23 or H32, both are same, because therefore we want to calculate only one. Okay, calculate H23. Okay, understand point? Do you understand? That is, if this psi 2 and psi 3 itself an SILC, they do not interact, then their integral, that is H23 or H32 is equal to 0. So if we want to understand, if we want to find out this psi 1, psi 2 and psi 3 interact, we have to calculate H23 or H32. I am calculating H23. What is H23? Integral psi 2 H cap psi 3 d2. Okay, then what is psi 2? Integral psi 2, what is psi 2? Psi 2 is equal to 1 by root 3. Okay, I think it is, yes, it is 1 by root 3. Okay, 1 by root, yes, it is 1 by root 6, 251 minus 52 minus 53. That is psi 2. H cap, phi 3, what is phi 3? 1 by root 2, phi 2 minus phi 3. That is psi 3 into d2. Calculate this one. That is equal to 1 by root 6 into 1 by root 2. That is, we can write 1 by root 12 into integral 251 h cap phi 2 d2. Okay, that is 2. This 2 we can take outside. This is 2 into integral phi 1 h cap phi 2 d2. Okay, minus 2 into integral phi 1, here phi 3, phi 1 h cap phi 3 d2. Okay, then minus phi 2 here, minus integral phi 2 h cap phi 2 d2. Then next phi 2 phi 3, minus minus plus, plus integral phi 2 h cap phi 3 d2. Then again minus here, I am writing here minus minus phi 3 phi 2 phi 3 into h cap, sorry, integral phi 3 h cap phi 2 d2. Again minus minus plus integral phi 3 h cap phi 3 d2. That is our equation. And here this term phi 1 phi 2, this is beta. Here also 2 into phi 1 phi 3, it is also beta. Phi 2 phi 2, it is alpha. Phi 2 phi 3, it is beta. Phi 3 phi 2, beta. Phi 3 phi 3, alpha. Then we can solve this one. This is equal to 1 by root 12 into, here it is 2 beta minus, again it is 2 beta, here 2 is here, 2 beta. Then this is minus, no, oh yes, it is minus, again minus alpha, again it is plus beta, again minus beta, plus alpha. Okay, that is our equation. Okay, that is 2 beta minus 2 beta cancelled, minus alpha plus alpha cancelled, plus beta minus beta cancelled. That is, this is equal to 0. That is, this H23, that is integral psi 2 h cap psi 3 d2 is equal to 0. What does this mean? This means that psi 2 and psi 3 do not interact. I already told you, if they interact, then H23 not equal to 0. If they do not interact, then H23 is equal to 0. Here we got H23 is equal to 0. That means psi 2 and psi 3 do not interact. That do not interact means this psi 2 and psi 3 itself is an SALC. Okay, psi 2 and psi 3 do not interact. Therefore, these SAGOs are itself SALC. If SAGOs do not interact, they itself forms SALC. That is our point. And how we find out they interact or not? We calculate their interaction energy, H23. Okay, H23 is not equal to 0, they interact. If C is equal to 0, they do not interact. We calculate H23. On calculation, we find that H23 is equal to 0. Therefore, they do not interact. Therefore, they itself forms SALCs. Okay, that is the point. Then, so we find that psi 2 and psi 3 do not interact. So they are itself are SALCs. And psi 2 and psi 3 are having energy of having a symmetry of E. They are a degenerate state. Therefore, energy of psi 2 is equal to energy of psi 3, and that is equal to 0. Sorry. So that is their same. They are not equal to 0. They are actually same. Okay. Energy of psi 2 and psi 3 are same. So we want to calculate the energy of psi 2 and psi 3. We want to calculate any one of them because the energy of other is same. So the other point is that if they do not interact, our determinant, that is this determinant, that is H22 minus E, H23, okay, H23 32 H33 minus E is equal to 0, and this can be considered as a one-dimensional, can be split into or can be blocked into one-dimensional determinant because they do not interact. So if they do not interact, we can block factor into one-dimensional determinant. Okay, then that is this can be block factored into one-dimensional determinant because they do not interact. Therefore, we can write H22 minus E is equal to 0 and H33 minus E is equal to 0. Okay, then Psi2 and Psi3 have same energy. Therefore, we want to calculate only one of them because other is same. So we take this equation H22 minus E is equal to 0. So this is our equation H22 minus E equal to 0. Therefore, E is equal to H22. What is H22? Integral Psi2 H cap Psi2 d2. Okay, that is what is Psi2? Integral Psi2 is equal to 1 by root 6 into 2 phi 1 minus phi 2 minus phi 3. Okay, H cap into again Psi2, that is 1 by root 6 into Psi2 is equal to 2 phi 1 minus phi 2 minus phi 3. Okay, that is our integration d2, and that is equal to 1 by root 6 into 1 by root 6. We can take 1 by 6 outside. Integral integral 2 we can take outside. This is 1 by 6 outside. 2 into integral phi 1 phi 1. So phi 1 H cap phi 1 d2. Okay, again minus 2 into integral phi 1 H cap phi 2 d2. That is this phi 1 and this phi 2. Again here minus is here, minus again 2 integral phi 1 H cap phi 3 d2. Okay, plus again and next this phi 2. Therefore, this is not plus, this is minus integral phi 2 H cap 2 is already here, also 2 is here. So 2 we can take outside. H cap phi 1 d2. Again minus into minus plus integral phi 1 this phi 2 and here also phi 2 H cap phi 2 d2. Okay, next to this phi 2 and this phi 3. Therefore, again minus into minus plus. So plus into integral phi 2 H cap phi 3 d2. Okay, again next is minus phi 3 and this phi 1. Again minus here 2 into integral this phi 3 this phi 1. So phi 3 H cap phi 1 d2. Next is minus into minus plus integral phi 3 H cap phi 2 d2. Again plus integral this phi 3 and this phi 3. Integral phi 3 H cap phi 3 d2. Okay, then this term phi 1 phi 1. Therefore, it is alpha. Phi 1 phi 2. This is beta. Phi 1 phi 3. This is also beta. Phi 2 phi 1. This is beta. Phi 2 phi 2 alpha. Phi 2 phi 3 beta. Phi 3 phi 1. It is also beta, and phi 3 phi 2. This is beta, and phi 3 phi 3 alpha. Therefore, we can reduce, that is E is equal to 1 by 6 into 2 into alpha here, 2 alpha, again minus 2 beta, again minus 2 beta, next again minus 2 beta, this one, n plus alpha, and this one plus beta, again minus 2 beta, again plus beta, plus alpha. Okay, actually there is a mistake here. It is not 2, it is 4, because this 2 into this 2, 4 here, therefore it is 4 alpha, 4 alpha. Okay, then this reduces to 4 alpha plus alpha, therefore 6 alpha. So we can write energy is equal to 1 by 6 into 6 alpha, and beta minus 2 beta minus 2 beta minus 4 beta minus 6 beta, this plus beta and minus 2 beta, this is cancelled, therefore minus 6 beta. Okay, and that is equal to alpha minus beta. That is energy of psi 2 is equal to energy of psi 3, because they are degenerate, is equal to alpha minus beta. Okay, so we get the energies of the SILCs, and okay, that is we got energy of psi 1, MO psi 1, energy of MO psi 1 is equal to alpha minus 2 beta. Okay, not alpha minus 2 beta, is alpha plus 2 beta, and energy of psi 2 is equal to energy of psi 3, because they are degenerate, that is equal to alpha minus beta. And you know that alpha is the energy of the atomic orbital, beta is the energy of interaction of two atomic orbital. Okay, and we take alpha normally as 0 of energy, because they have the energy of the atomic orbital, that is the middle point. And energy of interaction, when two orbitals interact, energy decreases, therefore beta is always minus. Okay, therefore beta is always minus, alpha is taken as 0, or alpha is the energy of atomic orbital, they are also actually negative. Okay, alpha is negative, beta is also negative, therefore alpha plus 2 beta has lower energy than alpha, or we can say it is a lower energy, or we can say alpha plus 2 beta has a lower energy of 2 beta than energy of atomic orbital. But here alpha plus beta, sorry, this is alpha minus beta, beta is minus, so minus into minus become plus, therefore it has higher energy. Okay, therefore psi 1 is the bonding molecular orbital, psi 2 and psi 3 are the anti-bonding molecular orbital. So we can write the energy diagram. This energy is alpha, lowest energy, that is alpha plus 2 beta. This is next step, that is alpha plus beta, and this is alpha, energy of atomic orbital, and this is alpha minus beta. Okay, and this alpha plus 2 beta is a non-degenerate set, it has only one molecular orbital. Alpha minus 2 beta is a degenerate set of 2 molecular orbital. Okay, so it has higher energy, it has lower energy. Therefore, in cyclopropenyl cation, this is our system, cyclopropenyl cation, it has only 2 electrons, and this 2 electron occupies in this bonding molecular orbital. Therefore, cyclopropenyl cation has a lower energy of 2 beta. It has a lower energy, is lowered by 2 beta. Okay, therefore it is the actually this is the delocalization energy. Okay, anyway, this is the molecular orbital energy level diagram of cyclopropenyl cation. Okay, so in this video we have calculated, we have determined the molecular orbitals and their energies. Energy of molecular orbital psi1 is equal to alpha plus 2 beta is a non-degenerate bonding molecular orbital, and energy of the other psi2 and psi3, they are degenerate molecular orbital, their energy is higher. They are alpha minus beta. Alpha minus beta is higher energy, alpha plus 2 beta is lower energy. Okay, we calculate energy, electrons are filled. That's over. Our section is over. Then the coefficient, we want to determine actually the coefficient. Here we need not want to calculate the coefficient because here there is no interaction between psi1 and psi2. If they interact, we want to calculate psi1 and psi2, then that is a tedious procedure. We want to use computational techniques to calculate the coefficients of the linear combination. Here no needs, we already got the energies of the molecular orbitals. Okay. I think you might have understand a little bit of this topic. Please read the textbook very well and explore more. Okay, thank you.